Thank you, everyone. I am delighted to be here today. I'm delighted to be in St. Petersburg. It's a city that has for years been on my list of places I would like to visit, and I had never had a chance before. So this is a really wonderful opportunity for me, and I'm very flattered that all of you have stayed around for the last talk of the conference. I have been to many conferences where people caught their planes and went home before the last talk, and so when I saw I was at the end of the program, I was worried, and I'm very happy and grateful to see you here. I'm hoping to talk for the next 45 minutes or so about a topic that is both somewhat old, about 10 years old, and fairly new. So it's a combination of work that was done by my then graduate student Bill Scherer when he was in our department about a dozen years ago, and he and I worked together with Doug Lee, who many of you will recognize as the principal architect of the java.util.concurrent libraries, and we thought we'd sort of finish this topic up, but then a newer student I had by the name of Joe Israelovich 3 or 4 years ago picked up on this topic and did some more work on it, and I'll be including that in the talk as well. So my thanks to all of those co-authors for the work I'm going to be talking about. As you saw on the first slide, I am from the University of Rochester in the state of New York in the United States. For those of you who are curious about where that might be, here's a picture. You'll probably recognize the outline of the Great Lakes. Rochester is at the middle of the south shore of the easternmost Great Lake, Lake Ontario. The closest big city is Toronto in Canada. We're almost 600 kilometers from New York City. So when I say I'm in New York, people think New York City, but really it's just New York State. There is an aerial picture of the university campus. You can see the bend of the Genesee River that goes around the campus, and often the background is the skyline of the downtown of the city, and the blue along the horizon is Lake Ontario. It's a lovely place. The Computer Science Department is a great place to work. We were founded back in 1974, and we're still one of the smallest top quality departments in the country, with about 20 tenure-track faculty members and 70 or 80 PhD students, as well as a master's and bachelor's program. We're probably best known for work in AI. About half of my colleagues do artificial intelligence work, but we also have very good work in theory of computation, in human-computer interaction, and of course, in parallel and distributed systems, which is my own area. A couple of slides of background. Forgive me if this seems like kindergarten for a moment. Most of us realize that uniprocessors stopped getting faster around 15 years ago. And since then, all but the most basic processors have had multiple cores on chip. And any program that wants to make full use of the processor needs to be written to make use of multiple cores, which of course was the first time in a couple of generations that speed improvements for programs depended on rewriting the source code instead of simply recompiling it for a newer processor architecture. When you write a multi-threaded program to run on a multi-core machine with shared memory, your threads interact by sharing data structures. All the data structures that you learn about in a CS2 course: stacks, queues, linked lists, priority queues, hash tables, the whole zoo of data structures. And I'll be using queues as the principal example in this talk, though many of the ideas would generalize to lots of other data structures as well. Queues, of course, are very important in parallel programs. You can think about an e-commerce application, for instance, that has some threads devoted to taking requests off of the network, and then some threads devoted to business logic, some threads devoted to interacting with the database, and they work like stages on a pipeline and pass work from one to the next via some sort of parallel queue. So we have multiple producer threads putting things into a queue. We have multiple consumer threads pulling things out of a queue, and we would like the behavior to be what we expect of a sequential queue. That is, it appears that the enqueue and dequeue operations each occur atomically in some total order that gives us the behavior we normally associate with first in, first out semantics. So let's think in a little bit more detail of what that might look like. If we have a sequential queue, a traditional one in a a single-threaded program, the version of the queue that has nothing in it might consist simply of a head pointer and a tail pointer, both of which are null. That's picture 0 above me. If we have one item in the queue, the head and the tail might both point at it, and its next pointer might be null. If we have 2 entries in the queue, the first one points to the second one has a null next pointer, etc. If we want to enqueue an item into the data structure, we would transform it from state 0 there to state 1, or from state 1 to state 2, or from 2 to whatever would come next. But concurrent updates aren't safe, of course. If thread 1 tries to dequeue element A and thread 2 simultaneously tries to enqueue element B, all sorts of bad things can happen. And on this slide, I've shown one possible interleaving, where thread 2 begins by reading the tail pointer, the little red circle up there. It then assumes that the next pointer on node A is null because the tail pointer was pointing at it. It creates a new node B, and then before it gets any farther, thread 1 comes along, reads the head pointer, reads the tail pointer, notices that they are the same, so there's really only one item in the queue, and it decides that it should set head and tail to null and take that item home with it. But before it does so, thread 2 continues, sets A's next pointer to point to B, then thread 1 goes ahead and sets the things to null. Thread 2 sets the tail pointer to point to B. Thread 1 deletes A, and at this point, our data structure is just completely broken. So we need to do something to make the operations atomic, and probably almost everyone in the room has written multi-threaded code in Java where you use synchronized blocks to do this, or synchronized methods in a class, in order to make your operations appear to happen atomically from the point of view of every thread other than the one that's executing the code of the operation itself. Unfortunately, lock-based code, or synchronized block-based code, performs very badly if the scheduler in your virtual machine or your operating system suspends a thread while it's holding a lock that is needed by other threads. So if thread A tries to insert something into a queue and gets halfway through its operation and has the core taken away from it by the operating system, then no other thread can perform an operation on the queue until A comes back again. And it's not unusual for an operating system scheduler to have a granularity of milliseconds. So millions of cycles could go by before the thread that holds the lock wakes up and allows anyone to continue again. So to remedy this, it's desirable in many situations to build non-blocking data structures that are not based on locks and in which no reachable state of the system makes it impossible for any thread to continue to make forward progress. That is, any state you can reach, if my thread is allowed to continue executing, it can make forward progress in a non-blocking algorithm. That means that any reachable state of the system corresponds to some clear, unique, unambiguous, abstract state of the data structure. So I can look at the bits in memory for a queue at any time and say, clearly, the following items are in the queue in the following order. There should never be any ambiguity about that. I should never have to know where in its code any thread is executing in order to determine what the state of the queue is at this moment. Devising a data structure like that is quite tricky. And people continue to publish papers about non-blocking data structures, many of them a year today. And this has been going on for a long time. The trick is to make the operation appear to happen instantaneously. So there's some instruction that gets executed partway through the code of the operation that is the instruction at which the operation appears to take effect. Often, but not always, that instruction is a compare and swap, a hardware instruction that replaces a memory value with some other value if the previous value was the one that was expected. And if you're programming in Java, as I assume many of you have, the library API for that instruction is the compare and set method. So r.compare and set of e and n says, please take reference r, check to see if it points to e, and if it does, make it point to n instead atomically. So I'm claiming that you can use a compare and swap in many algorithms to get the effect of the operation happening instantaneously. But of course, the operation actually does a great deal more than just that one replacement of one word in memory. So the trick is to essentially divide your operation into phases. There's an initial phase that is just planning. Thread is figuring out what to do, and its planning is harmless. It does not get in the way of any other thread. Then there's the one instruction at which it happens, and then there may be some cleanup, some things that need to be done to finish putting the data structure back into a convenient state for the use of other threads. But crucially, that cleanup work can generally be done by any other thread. It doesn't have to be done by the thread that initiated the operation, so that if it gets preempted immediately after the linearizing instruction, other threads can do the cleanup on its behalf. And there are non-blocking algorithms for many, even most commonly used data structures, and a lot of them are available in the standard library for Java or in commercial libraries that you can get from various vendors. So using a queue as an example, here is an illustration of the operation of the Mikhail and Scott queue, which was devised by my then graduate student Magid Mikhail back in the early 1990s. Magid had a long career at IBM after he graduated from Rochester, and then maybe about 4 years ago he moved to Facebook, and he now works on the data center infrastructure for Facebook. In an MNS queue, we have a head and a tail pointer, but an empty queue does not have 0 nodes in it. An empty queue has 1 node in it, which we call the dummy node. So there's always at least 1 node in the queue, but if it's only 1, it won't have any data in it. The dummy node has a next pointer that is null, and both the head and the tail point at it. If your queue has some actual data in it, then there will be a sequence of items following the dummy node all the way through whatever node is pointed at by the tail pointer. And in this picture, we've got the dummy node and then nodes A through Z, some arbitrary number of them that are in the queue. New nodes get inserted at the tail after Z there, and old nodes get removed at the head, starting with A. To perform an enqueue operation, we actually perform 2 compare and swaps. First, we use one compare and swap, illustrated with a kind of curvy arrow there, to change the next pointer of the tail node to point to a newly created node instead. So there's the planning stage in which we look at the queue and see what state it's in, and allocate this new node A, put the value into it, set its next pointer to null, and then we're ready for the linearizing instruction, which changes the next pointer of what had been the last node in the queue. So now in this picture, that last node points at A, and the cleanup is the tail pointer, because the tail pointer doesn't point to the right place right now. But we can tell that it needs to move because it points at a node whose next pointer is not null. And if any thread ever finds the queue in a state where the tail pointer points at a node whose next pointer is not null, then that thread can change the tail pointer to point to where the next pointer of the last node points in order to put the queue back into the appropriate state. And that's illustrated in this picture here. To perform a dequeue, we operate at the other end. We read the head pointer, we read the next pointer of the dummy node, we read the value out of the node after the dummy node, and then we use a CAS, a compare and swap, to move the head pointer from the dummy node to the node whose value we just read. We have to read the value before we do the compare and swap, because as soon as we do the compare and swap, our dequeue operation has happened. And any other thread could come along, and before we get to even execute another instruction, that thread could remove the next node from the queue. So we must have read our value out of that node before we do the compare and swap. Once we have done the compare and swap, the node that we read the value out of becomes the dummy node. By definition, the dummy node is the one that the head pointer points at, and now the dummy node itself can be deleted. But what I haven't talked about really is what happens when you try to dequeue from an empty queue. The natural default is to say, we return and say, sorry, there wasn't anything there. And often that's what you want. If you're writing a parallel program in which you periodically need to look for possible work to do, but you have other stuff you can do if there isn't a request coming in, you look to see if there's a request, and if there isn't, you go do something else. But there certainly are algorithms in which your only job is to service requests. So if there's nothing in the queue, you need to wait until there is something in the queue that you can take out and work on. And that's hard to do in a non-blocking data structure. Traditionally, it was impossible. The assumption in the entire literature of non-blocking data structures was that all methods of a non-blocking data structure have to be total. That is, applicable in all states of the data structure. No preconditions. So you can't have a precondition of the queue is non-empty. You have to be able to operate in any situation and work in a non-blocking manner, which means you return in a bounded number of instructions regardless of what other threads are doing. So if there's nothing there, you return and you say there's nothing there. So if we're going to use this in a program where we want to wait until there's something available, then we need to do something else. If we were working with locks, the natural thing to do would be to use some sort of thread sleep and wake up mechanism. And most of you have probably done that. In a synchronized block, you can do a wait. And if you do a wait inside a synchronized block, then the virtual machine puts your thread to sleep and releases the lock so that other threads can come along and put something into the queue for you. In a non-blocking queue, this traditionally hasn't been possible, so people program with a busy wait loop instead. They create themselves a loop and say, attempt to say something, to take something out of the queue, and repeat until what you get back is not a null pointer. That works, but obviously it wastes cycles. It causes contention on the data structure. If somebody else is doing modifications to the queue, then they need the cache lines of the queue in exclusive state in their cache, and every time you peek at the queue, you pull it back to shared state in order to get a copy in your cache, and then they take a cache miss the next time they try to access it. So not only are you wasting cycles, you're getting in the way of the thread that needs to make progress in order for you to get the condition that you want. So it's kind of doubly bad. You get high contention, and you get also no guarantee of fairness. So suppose my thread comes along and tries to take something out of the queue, and there's nothing there. So I go into a loop, and I start trying again. And after I've done the loop around and around a couple of hundred times, some other thread comes along, and it tries once. And it gets there at just the right time, and it gets the new element, and I stay in the loop. That's not very fair. Maybe I don't care about fairness, but maybe I do. If I'm in a program where the fairness matters, then I'd like the thread that's been waiting a long time to get the data when it finally becomes available. And of course, I do that if I was using wait in a synchronized block, because most virtual machines will order the waiting threads by the time at which they waited. I don't guarantee that, but it usually happens. So that's where dual data structures come in. All the talk up to now has been kind of introduction, and now I can tell you what a dual data structure is. It is a data structure that symmetrically can hold data or reservations, which are requests for data. And the idea now is that if you're trying to take something out of the queue or out of any sort of container, and it's empty or it doesn't have the kind of data you want, then you insert a reservation instead. So in the simple case, where any data would be acceptable to you, the data structure will hold either data items because there have been more producers than consumers over time, or it will hold reservations because there have been more consumers than producers over time so far in your program. And over the course of execution, it may flop back and forth between a state in which it's full of data and a state in which it's full of reservations. Crucially, the data structure gets to decide which reservation to satisfy when a producer comes along and there's multiple consumers waiting. So the data structure can be designed to control fairness. It can say, we are going to give the incoming data to the oldest waiting thread because that's fair. Or it might say, we're going to give the data to the newest waiting thread because it's the one that's most likely to have a hot cache. Or it could say, my threads have priorities, and I'm going to give the data to the thread that has the highest stated priority. And all of those can be programmed into the data structure if you are explicitly representing reservations. When you come along to enqueue data, you look at the data structure. If it has data in it, you add your data. If it has reservations in it, you take a reservation out instead and satisfy it. Similarly, if you come along to consume data and you find that the queue is full of reservations, you just add your reservation to it. And if it's full of data, you take a datum out and use it. So there's actually, in most of these algorithms, complete symmetry between data and reservations. And the code for the two is exactly the same, with just the identities of data and reservations reversed. We have developed, about a dozen years ago now, dual stacks and queues, also synchronous variants. How many people have heard of the synchronous queue class in Java? Maybe a third of the audience, okay. In a synchronous queue, not only do consumers wait until data is available, producers wait until a consumer is available to take it. So producers and consumers pair up. They both arrive at the data structure, one gives the data to the other, and they both return. There's also an exchanger class in the Java library that came out of our group in which two threads show up, they both provide data and give it to the other. So it's a swap mechanism, a synchronous swap between two threads. It doesn't have as many uses, but there's some algorithms in which it's quite handy. We have also more recently developed dual versions of the linked concurrent ring queue, or LCR queue, of Morrison and Affect, which is the fastest known concurrent queue of any kind on any machine. And we've also developed a generic construction that will allow us to create a dual version of almost any concurrent container. In fact, using one container for data and the other for reservations so that you can have a different policy on the two. Maybe first in, first out for the data, and last in, first out for the reservations. I'll keep using the queue as an example for the next few slides. So here's what a dual queue looks like. Again, when we're trying to remove data from an empty queue, we'll enqueue a reservation instead. And when we're enqueuing, we will satisfy an existing reservation if there is one. Otherwise, we'll add our data. In the queue itself, pointers to nodes will tell you whether the node you are pointing at is a reservation or a datum. And this depends on an idea that works easily in C and C++ and is a little bit trickier to do in Java. In C and C++, it's almost always the case on any architecture that a pointer points to an even address. In fact, it probably points to an address that's evenly divisible by 4 or 8 or even 16, so the bottom few bits of the pointer are always 0. That means we can use those bits for something else, as long as we clear them before we actually try to dereference the pointer. And that works fine in C and C++. It's not allowed in Java. The virtual machine won't let you do that. So any classes in Java that want to use this technique have to introduce an extra level of indirection for a tagged pointer. It's doable, but it's a little bit slower. All right. And again, as I mentioned, there is symmetry between the enqueues and the dequeues. Here's a picture for the dequeue operation. First, if I'm trying to take data out of the queue, I look to see whether it's empty or full of reservations. In other words, whether it's in a state where there is no data for me to take. If neither of those holds, then there's data there, and I try to take it out exactly as I did in the previous code. On the other hand, and at the same time, of course, if the tail pointer needs to be fixed up, I do that. If the queue is empty or has reservations in it, then I need to do something else. So in the empty case, I actually add a new dummy node at the tail. Remember, I wanted to take data out. The queue is empty. I can't take data out, so I put a new dummy node into the tail of the queue instead, using the same enqueue algorithm that I did before. And here I've colored that node pink just so you can keep track of it. Then we spin on the old tail node, which was the dummy node. And when the queue holds reservations, the real dummy node is at the tail end. So here's a picture of a queue that has reservations in it, colored in the cyan color, and the dummy node is at the tail at this point, indicating that the queue holds reservations. To enqueue, we read the head and tail pointers to see if the queue looks like it's empty or has data in it. And if so, we just put the data into the queue the same as we did before. Otherwise, we try to satisfy a reservation. To satisfy a reservation, go back to this picture here, we would look at one of the cyan nodes and try to link up with the thread that is represented by that node. And in order to do this, we actually write into the node, into a field that that thread might be spinning on. So let's think for a minute about how the thread is going to wait. We have two options. It could wait actively by spinning, or it could wait passively by yielding the processor with a wait. The spinning case is the easy one to describe. A waiting thread that came along and needed to put a reservation into the queue inserts one of these cyan nodes and then starts reading a field of it over and over and over. And that may sound a lot like the code I had a minute ago where you tried to take something out and it said there's nothing there and gave you a null value, and you therefore knew you had to try again, so you went around the loop again. The difference is that in that previous example, you were reading fields that everybody else needed to use. And so you were getting in other threads' way, and you were imposing memory traffic on the program, tying up coherence traffic in the cache coherence protocol. In the Dualqueue, if you're spinning on a node that you inserted into the queue, nobody else is accessing that cache line. So it sits in your L1 cache. It's not in any other cache in the system, and you can spin on it without bothering anybody. So the spin here is harmless, which is very, very different from the spin that we had before. Harmless, at least in the sense of causing any slowdown for anybody else. It is, of course, wasting cycles. So if you want to avoid wasting cycles, instead of putting a node into the queue that says, this has not yet been satisfied, and spinning on it until that value changes, instead, you put an entry in the queue that says, here's the semaphore that I am sleeping on. And then you go to sleep. And when another thread comes along, instead of changing the value of a word that you're reading the value of, it posts to the semaphore that you were sleeping on and wakes your thread up. Okay. Updating a reservation node to wake a thread up is done with a CAS so that we arbitrate between producers that are trying to do a wake up, and exactly one of them performs the wake up. Crucially, that modification to the node is made in place. So we have simultaneously woken up the thread that was waiting by changing the value that it's spinning on, and marked the node so that every other thread in the system can tell that that reservation has been satisfied. And it's very important that those two things happen together. The thread wakes up, and the node is clearly no longer belonging in the queue, and it can be removed from the queue by any thread. You can imagine algorithms, which I would not like, in which a thread would remove the node from the queue and then wake up the waiting thread that it belongs to. Because if you did that, then I could take the node out of the queue and get descheduled. If I take it out and the operating system puts me to sleep while I'm holding it, but before I woke up the thread that it belongs to, then the thread that it belongs to is blocked. And we don't have a non-blocking data structure anymore. So in order for this to continue to be a non-blocking data structure, I need to effectively take it out of the queue and wake up the thread that it belongs to in one step. And I do that by marking it in a way that allows any other thread in the system to take it out of the queue. All right, so we have this dual queue. We also have a dual stack. As part of his thesis work, Bill invented data structures that would be a queue for data or a stack for requests, and one that would be a stack for data and a queue for requests, just to see if he could. And it turns out it was fairly straightforward to mix up those two policies if you wanted. And then we got in contact with Doug Lee, who was working on what was then called JSR 166. Maybe some of you have heard that. It was the Java community project that turned into the java.util concurrent libraries and became standard in Java 5. Doug was working on the version for Java 6, and our dual data structures got added into Java as of Java 6. The classes were useful in and of themselves. The API is available for any program that wants them, but they also turned out to be very useful, particularly the synchronous versions in the executor library. How many people have used executors in Java? Okay, good. So this is the fine-grained task programming model in Java, where you create lots of callables or runnables and you put them into a data structure, and something in the library takes care of calling or running them for you. Pairing up work to do with threads that are going to do the work is a perfect job for a synchronous queue. And the synchronous queues that were in the library prior to Java 6 were a bottleneck. And when they were replaced with the dual versions that Bill had devised and worked with Doug to perfect for Java, we got significant performance improvements. The dual stack was 3 times as fast as the previous so-called unfair executor, and the Dualqueue was 14 times as fast as the previous so-called fair executor, which was itself much slower than the unfair executor. So overall, the throughput of the executor library went up by about an order of magnitude in Java 6 as a result of these data structures. More recently, my student Joe Izraelovich became intrigued with some work that had been done by Morrison and Affek to make very fast queues. And in the process of studying those queues, he got re-energized around dual data structures and realized that it would be nice to be able to combine more or less arbitrary policies for data, in other words, orderings, first in, first out, last in, first out, priority, whatever. Be able to combine arbitrary priorities for data with arbitrary priorities for reservations or anti-data. He develops a technique to do this, which we published in ACM Transactions on Parallel Computing a couple of years ago. And I'm not going to have time to go through exactly how that works, but if you're excited about the topic, I encourage you to go check out that paper. So, how exactly does this work? To pair, I can't give you the details, but I can give you the hint. To pair an arbitrary data structure with an almost arbitrary reservation data structure. And the almost part is that the reservation data structure has to allow you to peek and see what the first reservation is that you would take out if you wanted one right now. And that ability allows you to kind of tie together the two data structures. So we insist that the reservation container has to have this peek operation that returns a pair of values. One of them is the reservation that would be removed if you wanted to, but you're not removing it. And the other is a key that allows you to tell later whether that is still the right reservation or not. So in the sort of generic construction, you peek at the reservation container, then you look at the data container. And let's say you're a dequeuer. So you peek at the reservation container, then you go to the data container, and if there's data there, you take it and go home and just forget about the reservation container. But if the data is empty, then you go back to the reservation container. So the ability to peek lets us satisfy reservations in a way that other threads can help. So we peek at the reservation, we sort of publicly say, this is the reservation that we would use if we needed one. Then we go to the data container, let's say we're a producer this time, and there's no data in there, so we need the reservation, we need to wake up that thread. But if we get preempted, it's important that anybody else be able to wake that thread up. This sort of handshaking between the two data structures makes the wake up still non-blocking. The paper that I described a moment ago has this generic construction in it. It also has special purpose versions of the Morrison and Affect queue. And those special purpose versions maintain the very high performance of the queue. So probably most of you haven't heard about this queue. You should go learn about it if you're curious, because it is the fastest concurrent queue, faster than any lock-based queue. It's based on circular arrays, which of course are bounded, but then it has a linked list of them. So the idea is to use a fetch and increment instruction to find the next slot in the current circular array. And if there isn't any room, then you create a new circular array and link it into the list. And the tricky part is that the fetch and increment operation gives you a next slot, but doesn't tell you how you've lined up with producers if you're a consumer, or how you've lined up with consumers if you're a producer. So imagine this case where I have an array, I do a fetch and increment, which is an atomic operation that gives me the next slot, but I'm a consumer, and there have been a lot of consumers recently, so the consumers are already ahead of the producers. There is no data, but my fetch and increment just moves me farther and farther along the array. That was the challenge that prevented people for many years from making fast, unbounded array-based queues. Morrison and Affect figured out how to get around this by recognizing when you had cycled all the way around the queue, fixing it up if you could, but in the corner cases where you couldn't, just marking the queue as no longer usable, adding another one, and moving to that. They worked out all the corner cases. It's very fast, but very complicated. When we put in the dual version, we get the fastest known Dualqueue, and it is almost 5 times as fast as the Dualqueue that I showed you a few minutes ago when running on a machine that has a fetch and increment instruction like the x86. It's difficult to add to Java, so we haven't done that yet because it does a lot of pointer tagging, but it works great in C and C++. So to sort of summarize what I've been talking about for the last half hour here, non-blocking operations actually can wait. And this was the surprising conclusion of our work a decade ago, that it's not a nonsensical statement to say that I want a non-blocking data structure in which I wait when it's empty. It actually does make sense, and we can use these dual data structures to improve the performance of lots of containers on which threads may want to wait when it's empty. And the dualism gives us fairness at the same time, so that the data structure itself controls which thread gets data when it becomes available. And more recently, that we can combine arbitrary data and reservation data structures to produce whatever pair of policies you want. There are some future directions that might be worth exploring. I'm not actively working on any of these, but I would be interested in talking to anybody who would like to work on them. It's always seemed like we ought to have a dual priority queue. We haven't written one, but working with one of the non-blocking skip lists, for instance, as a foundation might be a good way to create a dual priority queue. We could also think about data structures that have predicates on remove, where instead of saying just give me the next datum of any kind, you could come in and say, please give me a datum larger than 100 if there is one. If they're all smaller, then I'll wait. Or maybe give me 4 elements, and if there's only 3 of them there, then I'll wait until the rest of them are available. We also could think about fast specific combinations. And if you'd like to read more about this topic, these are papers that you could go check out. And at that point, I will stop and entertain questions.
Yes, thank you. So, if anybody have questions, you need to put your hand up, and we will give you a microphone.
Hello.
Hello.
How do you deal with the situation when consumer placed the reservation and, for example, used the reservation with some kind of semaphore, but before the reservation was completed, this particular thread timeouted or otherwise died, for example? How do producer should deal with that?
We don't consider the possibility of threads dying. The code's not designed to cope with that. It's written on the assumption that all the threads sharing data are part of the same program. So the program may die, in which case all the threads go away. We don't care anymore. But you'd never have a case where an individual thread dies.
Thank you.
Okay.
Anything else?
Hello. I just tried to find some realization of these structures in the internet, but I can't. Is it possible or not?
To find the code?
Yes, yes.
So for the Dualqueues and stacks and the exchanger, you can find them in the Java standard library. So it's synchronous queue, so-called fair and unfair versions. The fair version is the queue, the unfair version is the stack. A stack is an unfair queue. That was not my fault, but that's the name that it has. And then the exchanger class is also in there. C code, there may be some on my website. I haven't actually looked in a while, so I don't remember whether we have the code posted or not. But there's a link to the synchronization project on my homepage at Rochester that has a good chance of having the code in there. Oh, the generic stuff, the arbitrary data and reservation policy code, that's certainly available, and the URL for it is in the paper in Transactions on Parallel Computing.
Maybe I have a off-top question, but you are author of a lot of papers and books and etc. What's the topic, on what are you working now, and do you have a plan for next decade?
I wish I could plan a decade at a time.
I hope.
No, I don't have a plan that goes ahead a decade. The 2 main topics that my group is working on right now are persistent memory and management of extremely fast devices. And these actually are connected topics. I am largely a systems person. I like to work across layers of the system stack. The persistent memory that's now available is Intel's Optane DIMMs and is likely to be joined by various other technologies from other vendors soon, is intriguing. It's extremely dense and low power, and we may simply use it to replace DRAM with much larger quantities of cheaper memory. So it may just be the thing that lets us have a terabyte of memory in our cell phones. And we may program with it exactly the same as we always did with DRAM. Or maybe not, because when you turn off the power, it retains its values, the same way that a solid-state drive or hard disk does. And that raises the possibility that you might choose to keep pointer-rich data in memory across program runs and even crashes. And if you do that, you need to think about what it means for a data structure to be correct in an execution containing crashes, because you want to be able to use it after the power comes back up. And it would be very bad, for instance, if you allocated a node to be linked into a list and you updated the pointer to point to it in your cache, and the cache wrote the pointer back to memory and hadn't written the node back to memory yet when power failed. Because then when you came back up again afterwards, you'd have a pointer that points to nowhere. So you need to make sure that writes back from the cache to memory happen in the right order when it matters. You need to figure out when it matters, because forcing the order all the time would slow your program way down. So there's a lot of work that can be done in designing data structures that are guaranteed to be usable after a crash. There's work that can be done in general purpose libraries to allow programs to build data structures that will be usable after a crash. And then there's all sorts of work that can be done in rethinking how we build file systems, how we build the buffer cache in the operating system, how we structure the layers of the storage hierarchy in the operating system, and how we test persistent data structures, how the memory allocator works. My group's looking at all this stuff around the idea that we might use persistent memory for pointer-rich data structures long term. So that's one topic. And the other topic is very fast devices. And they're actually connected by the fact that non-blocking memory kind of is a very fast device. Persistent memory kind of is a very fast device. So in a data center today, we have network interfaces that can communicate with other nodes in other racks at microsecond speeds and can send several million packets per second. And if you're trying to pump several million packets per second in and out of a network interface, you're not going to do that with one core. You need multiple cores. And you're not going to be willing to pay for the overhead of a system call on every packet. And because of this, data centers today, run by Facebook and Google and Amazon and everybody else, use direct access to devices from user space. The operating system maps the device interface into the user-level program, and the user-level program talks to the device directly. And this is still safe because every program talks to the device through a separate page. And those pages are set up ahead of time by the operating system. But now you have to ask what happened to fairness, because fairness was always the operating system's job, right? It's supposed to make sure that my program doesn't get 10 times the bandwidth of your program when we're running on the same machine, unless, of course, we contracted with the operating system to give me 10 times the bandwidth that you're getting. If the operating system isn't in the loop on every request, then it can't do that anymore, at least not naively. So our project is looking at mechanisms that allow us to trust library code and to give rights to library code that can be accessed quickly that the rest of the application doesn't have. So now I can do a subroutine call into the library to send a message, or perhaps to modify the values in a key value store that's in persistent memory. That's where it connects. Without the possibility that a stray pointer in my application could accidentally send a packet or trash the content of the shared memory. So if my program is under development and I don't trust it because it's got bugs in it still, but I trust the library, I can link the library into the program, and if the program makes calls into the library, then I can trust that the library will vet those calls in an appropriate way and verify that the parameters are correct and only do the right thing. And when I'm not in the library, I won't physically be able to touch the data. That mechanism can be implemented in multiple ways. There's hardware support that would make it really attractive, but even on current Intel machines, we can build it. using what's called protection keys for user space, which is a new feature that became available in the Cascade Lake model of Intel's processors. And actually, this very week, we had a paper at the Usenix annual technical conference that described how to do this. So if you're curious, go look for a paper that has Hodor in the name, the character from Great Game of Thrones. The Hodor project is our system for protected libraries on Linux, on x86 machines. And that was a much longer answer than you were asking for, but I'm excited about both of these projects, so I'm happy to talk about them.
Please, thank you.
You said that the dual data structures are symmetric for producers and consumers. So can this approach be used to build a bounded queue when producers block on a full queue? And will this require a second type of reservations?
That's an interesting question. So you block for two different reasons. I think it could be. We haven't tried that. It would certainly make sense. But you would need to have sufficient capacity to hold a reservation for every active thread. I don't see how you would make this work if you had a queue that could hold no more than 20 elements and you had 30 threads, because if they all needed to put a reservation in, there wouldn't be room. So we've only thought about it for data structures that are either unbounded or have enough space that all the reservations would fit.
Okay, it can be bounded for, say, 20 values, but it can potentially contain 30 nodes. Those will not contain.
I didn't mean pages, I meant data elements. So if the queue is small, you're interested in bounded queues, where if you try to put something in and it's full, you wait.
I'm interested in bounded number of values in the queues, not necessarily nodes or anything else.
You certainly could invent a queue that had a limit on the number of data elements that could be put in, but could have an arbitrary number of producers waiting to add more data or consumers waiting to take data out. I haven't thought about building one of those, but it would seem to make sense. I don't know of an application where the bound is important. I mean, maybe there is one. Normally we use bounded queues just because they're fast, and we have an application where we know that it's big enough.
They're usually used for contention control in the producer-consumer systems.
Okay, sure. That's an interesting idea.
Thank you.
Thanks a lot for an excellent talk.
Thank you.
My question is, most of the time you have to live with existing hardware optimized for commodity systems, but how ideal hardware look like from your point of view? What would you like to see as the ideal hardware for parallel and concurrent data structures?
Oh, gosh. There's all sorts of things that I would love to have hardware vendors do. Many of them, of course, are not practical. I mean, I'd like a processor that's infinitely fast, right? Can you give me one? In terms of practical things, it would be nice, for instance, to have available in user space the M-wait instruction of x86 processors, right? So that my thread could say, I want to effectively busy wait, but I don't want to consume any pipeline cycles while I'm doing this. So put my hardware context to sleep and wake me up when this cache line is lost, which is what M-wait does, and it's currently available only in the kernel. Alpha processors had this in user space. They called it quiesce, but alpha processors aren't around anymore. That would be nice. It would be nice to have lots of hardware contexts. That's not free, because every one of them takes space to hold a register set and various other bits of data in the core. But there are times when I'd like to have a lot of threads, most of which are not executing, but are sitting around waiting for something. So imagine that I could have 50 threads all doing an M-wait, just ready to go as soon as something came in, but actually not consuming any pipeline resources. That would be nice. Many of you may have heard about transactional memory. It's a topic that I worked on a lot over the last 10 or 15 years. There are features in hardware transactional memory that I would love to have that aren't available. In particular, I would love to be able to do non-transactional, non-speculative loads and stores in the middle of a transaction cheaply. There are all sorts of really cool things that you could do if that were available, and that should not be hard to add. But I have not yet been able to convince friends at IBM or Intel to do it.
Thank you.
Thank you for the talk very much. Nowadays, we have a different kind of data structures, different classes of concurrent data structures, like relaxed data structures, flat combining, dual data structures, etc. You said that, for instance, dual data structures we can see in Java 6, some data structures we can see in the next versions of java.util.concurrent. And what's your opinion? What's the nearest future of integration of different classes of current concurrent data structures in the near, for instance, Java versions in its core? Because there are a lot of research on different kinds of classes of such an algorithms, but we can't use some non-standard decisions in production.
That's a very open-ended question. I think you're kind of asking what do I think the next generation of the concurrency libraries is likely to look like, and I don't know. I'm not actually actively involved in creating those. I do follow the literature, of course, in concurrent data structures, and there are a lot of exciting things that are going on. Trends that I see that still seem to be active and are producing papers and will probably produce useful technology for production libraries include flat combining, which you mentioned, which is a really lovely technique for dynamically balancing the trade-off between concurrency and locality. And that's something that's increasingly important as we get machines that have a longer effective distance between processors. The dynamic between scheduling and waiting and busy waiting and descheduling is an important one, and I think there's a decent chance that we'll see data structures that are smarter about waiting for things in sort of the fashion that dual data structures do. There's been a lot of recent work on practical non-blocking data structures, particularly wait-free data structures. So I didn't go into detail about non-blocking progress in this talk, but there's actually different strengths of non-blockingness. The weakest one says, if everybody else holds still for a little while, I can finish my operation in bounded time. That's the weakest form of non-blocking progress. It's called obstruction freedom. Most algorithms do better than that. They say, even if everybody else is busy and actively doing things, I know that in a bounded number of my steps, somebody will finish something. The system will make progress. But the strongest version is called wait freedom, and that says, no matter what anybody else is doing, I know that I will finish an operation in a bounded number of steps. Wait freedom has historically been very hard to get, expensive. And there's been some very nice work that's come out of Eris Bertrank's group at Technion in Haifa recently in particular on creating practical wait-free data structures. He's not the only one working on this, but it has surprised me. I had thought for years that wait freedom was just not worth the effort. But there's some recent work that suggests it may very well be worth the effort, and it is potentially attractive for real-time applications where you want to be able to bound the amount of time it can take to perform any particular operation. It can also be really nice when you have some operations that need to do a lot of work, and in a merely lock-free implementation, the long operations keep getting restarted because they keep bumping into short operations that are in their way. And then the long operations can starve. And in a wait-free algorithm, the long operations won't starve, and that's very desirable. There was a paper by Dana Dreschler-Cohen and some others at PPOP in 2018 that showed how to add wait-free traversals and lookups to arbitrary concurrent trees, whether lock-based or non-blocking, which is a really cool idea, and leverage some previous work by Natarajan and Michal. So there's a lot of work that's still going on in fast, complicated, non-blocking data structures. And I suspect some of that will end up in standard libraries before too terribly long.